So today's agenda would be a little bragging that's like behind us, show of hands, which will hopefully drag you from the sleep. Because I've read a study where it was actually told that if you have like number of knowledge feeding sessions, at some point you need to really actively move your body. So with show of hands, like I'm hoping I'll at least achieve some of it. Then a history primer, setting context for what is actually memory model, why and from where it comes from. Then the memory model itself, the Java parts mostly. And finally, short advice and links, because a memory model is really a deep topic and there will be plenty of questions unanswered after this presentation. I'm sorry about that. So hands up, who knows who Gene Amdahl is? Okay, we have like 3 hands in the air, including my own. Okay, let's say who Gordon Moore? Who knows Gordon Moore? Okay, who doesn't know Gordon Moore? Okay, now we have the gymnastic parts going there. Leslie Lamport, without the E. Okay, who doesn't know Leslie Lamport? Okay. Who doesn't know Bill Pooh? And who does know him? Because I see that a number of hands didn't show up. Oh, come on. Some people missed the question. Sarita Adver, who doesn't know her? Okay. Hans Bem. Who does know Hans Bem then? I see we have a number of C people in the room. Martin Thompson, who doesn't know him? Again, you've come to a good talk. Alexei Shipilev, that should be easy. Who knows Alexei? A number of hands up. Very well. So, who here doesn't program? What do you do, if I may ask? Totally excused. Who knows Moore's law? So, guys, Gordon Moore is the author of Moore's law. So, next question would be, please. Please always works. Who knows Amdahl's law? Okay, so there are 4 people in the room who may actually be aware now that Gene Amdahl is the author of that law. Gustafsson? Yeah, I know I'm stretching. Pretty much nobody knows this guy. Who here feels confident that he can explain? Okay, I see one head shot up. So you really believe you can stand up here and explain concurrency versus parallelism? Yeah, I'm trolling. You won't be asked. Okay, good. Who believes he codes with mechanical sympathy? Well, that's actually, if you do not know Martin Thompson, I may skip this one, and this one. So a bit of context, which will kind of explain all those questions. Gordon Moore is a person, don't tell me. Well, here was a picture, but I guess it isn't here anymore. Gordon Moore is a person who founded Fairchild Semiconductors. For those of you who do not know, this is the company which actually made Palo Alto and Silicon Valley possible, because they started this. When Fairchild Semiconductor was founded, pretty much little to nobody wanted to work there, because they was like, what's with this remote location? If they would get the offer now, it would be like, but of course. His law is kind of self-fulfilling prophecy, because Moore is also one of the founders of Intel. So when he made an observation, it was backed by pretty much whole company. And with Intel setting standards on the market then, it later turned out to be something like a self-fulfilling prophecy. So, Moore's law. Right now, Gordon Moore, this very year, said that within a decade, Moore's law will stop being in effect. It will actually die. So what is the law? The law was that transistors in dense integrated circuit are doubled every year. So every year we cram more and more components into one integrated circuit, effectively doubling its power, its computational power. Now, this was revised in 1975 from 1 year to 2 years. That was pretty much the only change. And this is often shown on a very nice linear graph, which tells us that hardware is steadily progressing and it's steadily being more powerful than it was, doubling the computational power. All very nice. However, Gene Amdahl actually, and why was it actually a self-fulfilling prophecy? Because Intel set the trends for the market. So pretty much every other chip manufacturer, when they heard, well, Intel said so, they actually tried to make it so. So it wasn't really very scientific law. Gene Amdahl, who is one of the IBM fellows awarded by IBM, he coined a law in an article in 1967, and he's known for both IBM and Amdahl mainframes, and his law is saying that the speed up of a program depends on its sequential part. So if we have like 95% multiple, shall I close the door because I see that some of you are making strange faces? Yeah, okay. Yeah. Okay, so when it will become too hot for anybody, just wave at me and says, the door, the door, the door, the door, and I'll actually realize what you're about. So sequential fraction of the program actually limits the gains that we can have if we throw multiple processors at the program. Well, kind of obvious, right? And within the same article, because Amdahl's law is frequently taken out of its context, it's frequently said as, throw as many multiple processors as you can at the program and you will be really, really fast. And often, it's forgotten that Amdahl actually criticized that when he wrote the paper, because he stated that for over a decade, and notice the date, 1967, for over a decade over then, organization of a single computer was stated as something nearing limits. So something similar that we keep hearing now. If you read the papers or actually hear the arguments, it's pretty much the same thing. Now, it was then prophesied that only by interconnection of the multiplicity of computers, we may actually gain speed. So half a century later, we still keep hearing it. If you actually heard or have seen Brett Victor's presentation, The Future of Programming, your application will still be waiting for something. Then concurrency. But if you have like strictly sequential things which you can't make, which you can make independent, then yeah, go with parallel. In essence, you will want to take a look at your tasks. Imagine it as sort of a pipeline or an assembly line, factory line, however you will, and take a look at parts which you can actually delegate to someone else or run independently. So let's have an example. Let's say that I need to make a passport, get a passport, because my old passport is invalid, which is actually quite my case because I was supposed to speak at JavaDay Kiev 2 years ago, but a day before when I had every ticket actually booked up, I realized that my passport lost its validity. So yeah, if you want to actually go to JavaDay Kiev or Lviv and do the presentation, you need to have a passport. So how do you go about it? You may actually take the passport, or every data you need to get a passport, go to the passport office, and after you finished, you go home, you sit and start working on your presentation. This is strictly sequential. You do one step at a time. But perhaps you want to actually save up the time. So you go on with every data that you need to get a passport to the passport office. Now, you arrive at the passport office, and then when you wait in line, you pull out your laptop and you start working on your presentation. Now, this is concurrency. You're now actually being concurrent. By the time you actually end up, you close the laptop, you do the formalities, you get the passport, you come back home. You may then continue working on the presentation. If you want to be parallel, you need to have an assistant. So let's say I have two assistants, one very muscular, the other very handsome, or pretty rather, and the pretty assistant says that she will do my presentation, the handsome assistant will actually assist her, and now we have three independent executors doing the passport and the presentation. This is parallelism. Now, of course, with the parallelism, I also may do concurrency. Because perhaps when I'm at the passport office, they email me about a problem in the presentation draft. So now I can actually pull out my laptop and you get the drill. So, in a nutshell, comparing concurrency versus parallelism in terms which is better is either depends on the context or apples versus oranges, because they are kinda different. More cores. The core that you see on the screen has like 78, the processor you see at the screen has 78 cores. The company that released it, they aim for the 100-core processor within like few months. So, if you wondered whether the multi-core processors are reality, yes, we are pretty much in the multi-core era and we will continue to get more. And with this, it's time to introduce Mr. Leslie Lamport, who is he's so-called father of the distributed systems. Why? First of all, he coined the very definition of the distribution system. Then he started working on distributed system clocks. Then he also coined the happens before relation and number of others. So, what is the definition of a distributed system? It is a system where a failure of a computer you didn't know existed renders your own computer unusable. So, if, for example, I'm in a network with 3 computers and one computer is processing payments and I want to buy something, then if the computer that actually is processing payments failed, I may not know about its existence, but I will still not be able to purchase whatever I wanted to purchase because the payments will not be processed. So distributed systems are interesting in number of ways and are pretty much common nowadays. And with distributed system, there comes the problem of a clock. Because we humans, we believe that time is linear. First thing happened, second thing happened, and after this, third thing happened. Now, sometimes things happen like simultaneously, but still, on a timeline, you can still place those things in a happened before relation. So, with computer systems, the problem is that different systems have different clocks. Have you ever heard of a Heisenbug? So? Exactly. A bug that changes its behavior when you observe it. When I first read about Heisenbug, I was like, huh? Whoever came up with this weird shit. Now, how it's possible? And like 2 years later, I actually had a bug which was replicated by a tester on production. So I sat down to work on it, and yeah, I can reproduce it. Okay, so debug what happens. And I'm passing, everything passed. No bug. Okay, so perhaps I made a mistake in the reproduction scenario. So again, I'm passing the test. No, the bug is there. So debug, passing. After some pondering, I got to the real culprit. The database clock was 12 seconds slower. So when I was in the debug, the time still kept going. And by the time I got to the operation where the time difference mattered, the database clock was already up to speed, because it took me more than 12 seconds. Now, with distributed system, the problem is only bigger. You may have more and more cases like that. And Lamport actually noticed that we people want to have things linearly, even if it's hard to do so. So he coined a happens before relationship for a distributed system. Okay, let's go to Java. So, green versus native, why this slide is here? Ah, yeah, I recall it, sorry. First version of Java actually had green threads. The Java 1.1 had green threads which were later abandoned due to the fact that native threads actually had more capacity, more capabilities. So, when you take a look at multi-threading, it all depends on the CPUs. How many CPUs you have, how many cores your CPUs have, all that. So, with that in mind, it's kind of obvious that operating systems will be able to do multi-threading. Well, that's what they're for. They need to actually be able to make us use the CPUs effectively. So, OS scheduler, kernel, all that comes under native threading. You will have threads made available for you by operating system, whatever it is that you're using. Now, Java had green team, actually Sun back then. Sun had green team, and green team was responsible for Java threading. So they came up with the idea of not really native threads, but Java threads. They coded those threads, and from their name, those threads were named green threads. So if you ever wondered what the hell are green threads, those are Java threads. Now, the best thing about the green threads is that they happen in user space. If you know a lot about Linux, you know that there is a user space and there is the kernel space. Now, when your code actually goes from here to here, a number of things happen. Among them, for the switch, you're like wasting a number of cycles. How many cycles? That really depends on machine and architecture and distribution, but still, you lose cycles. Kernel space is the system space, so usual system user programs do not have access to it. Now, despite the lightweightness of the green threads, they later had been abandoned in next subsequent versions of Java because native threads just had more capabilities because they were more actively developed by kernel developers. I believe there also were issues with the green threads and Microsoft, but that's another story. So memory model works by examining each read in an execution trace and checking that the write observed by the read is valid according to certain rules. This slide will be somewhat hard, apologies, but the definitions are made simple later. So basically we examine reads and we take a look at write observed by that read and we check its validity according to certain rules. The rules are within Java language specification. Let's go on. Formal specification of how the memory system will appear to programmer, eliminating the gap between the expected behavior and the actual as supported by the system. This is the best memory consistency model definition I've found, and I found a number of them. This is also the only definition which is Java, not only Java related, but it speaks about pretty much every memory model. Memory model answers one simple question. What values can a particular read in a program return? As we can see so far, there are a number of really strange things here. So a read can return more than one value. My perception of a memory might be faulty, like there might be something going behind the scenes. Rather complex stuff. Now, finally, the JSR 133 frequently asked question, when asked what is a memory model, they answer that it defines necessary and sufficient conditions for knowing that writes to memory by other processors are visible to the current processor, and writes by the current processor are visible to other processors. Now, let me ask you an honest question here. Are these definitions easy? Well, I read them out loud. Are you able to follow? Any problems with understanding? Somewhat vague. Yeah, quite cool. So, In simple words, memory model examines reads. Whenever you read from, you want to know what value is something, you make a read. When you make a read, this is where memory model kicks in. It takes a look at writes. It checks write validity. So there are rules within which you may actually write something to variable. Now, it makes memory system appear consistently. Ergo, we know that memory system will be inconsistent at times. It tells you what values can a read return. So it plays with this inconsistency. It defines conditions for knowing what is visible to which processor. So, what is visible to each processor? If we have number of processors, the processors have numbers of cores. Now then, this kind of begins to click together. Most cores have cache layers. So you have a CPU. CPU have registers, but additionally, it has level 1 cache, level 2 cache, level 3 cache, and then main memory. So whenever we hit the bottleneck between the CPU and the memory, the von Neumann bottleneck, then we bypass all the caches and go straight to memory. And pretty much all which is in memory will be seen the same way by all the cores on the processor, and will be seen the same way by all the processors. Now, each core has 3 or 2 or 1 level of cache, depends on the processor. Now, the problem appears when, for example, the data in the caches are different per core, which will be for every core which is not common for all, for every cache which is not common for all the cores. Memory model defines who and when sees what, and there are strong and weak memory models, which basically tell you how much of a sequential consistency you will have with all the operations. So how much all the operations that pretty much happen on all the cores in all the processors will the system be able to present sequentially? So, when Java came in, it was the first language with built-in memory model. The guys didn't just want to let the CPU be handling their stuff, let the CPU manufacturers to enforce the memory model. They wanted to have their own memory model because Java was designed for concurrency. So, shout out, how was Java designed for concurrency? What construct in the Java language made it concurrent or enabled concurrency in any way? And hint, these are keywords, Java keywords. I've heard number of simultaneous, there was final, volatile, yes, synchronize, yes, excellent. So, those are the 3. Now, synchronize is easy, obtains locks and unlocks. Final, makes variable unchangeable. Volatile. Stronger read consistency, very nicely said. So volatile actually ensures that variable, when we pull it, it's fresh. Well, volatile actually ensures that the value will be in memory. So, problem was that the first memory model that Java came in with was botched. If you happen to have final variable, when you initialized it, you could actually see different value. When you had synchronized and used the construct so-called double locking, you could end up with thread being deadlocked, which wasn't supposed to happen. And volatile sometimes worked and sometimes it didn't. The problem was that the specification was too hard, and people who were actually implementing it, well, they did it how they believed it worked. So memory model is hard, and even now after Tiger came in, it's not really fixed. And there are 2 things being done. One is JEPS 188 and the other is Java Memory Model 9, which if you want to see how the memory model will change, these are your references. So the guy behind Find Bugs was the person who actually showed everybody that Java memory model, the original one, was broken. This led to actually JSR 133, which was incorporated into Tiger, which is Java 5. And since Java 5, the Java memory model works more or less consistently. He got help from Sarita Adve, who is basically a person behind a number of papers on Java memory consistency model. She is the author of the best definition I ever found. And she is also a person who, with Hans Bem, was working on the C++ and C memory model. Because while Java was the first language, it by no means was the last. Python already works on the memory model. I think in previous standard it was already included. C++ 11 has already a memory model. C11 also. So number of languages are actually getting into memory model because it's just that good. Now, optimizations that you can have. There is inlining of a function. There is actually unrolling a loop. You can actually expect that the compiler or hardware compiler, they will reorder your code, that they will actually remove what they think is dead end. So that code will actually disappear during the compilation. And one of the most interesting things are code branch predictions. So if you take a look at the code, we often write code in branches. So for example, if or else, the most common example. Now, compilers can often predict that else will never be executed. So the final code may not have the else branch. Where it matters, it actually matters on the compilation level. So for example, Java's, Jython, whatever compiler you're using. Then the just-in-time compiler or hotspot compiler, which is the JVM stuff already, they will also perform optimization. And of course, hardware will also perform the optimization because hardware memory models are also in existence. Now, each time, for all those free optimization, this is done by a different team of people. And while Java's people and JIT people often talk together because they are employed by the same company, you can't tell the same about hardware people. Now, this is the illumination for the caches that I was talking about earlier. So, memory is over here. Now, here we have level 3 cache, which is common for all cores across the CPU. Now, here we have other caches, and finally, registers, which are like fastest ever. Now, this is one CPU. So if you have number of other CPUs, then memory is pretty much the first line that they usually talk through. Now, data distance rather matters. Why? 1,000 nanoseconds is 1 microsecond. 1,000 microseconds in 1 millisecond. Now, if we take a look at level 1 cache references, so if the CPU can pull out data from level 1 cache, it takes him half of a nanosecond. In comparison, if it pulls it from main memory, let me see, 100 nanoseconds. If we take a look at, and we want to take the data from main memory, this is 100 nanoseconds. Now, if we want to take it from the disk, 150 microseconds for random read from solid state drive. If you have the old disk with the spinning cylinders, it's even worse. 10 millisecond disk seek. Now, with that in mind, let's take a look at some optimizations. 5 nanoseconds is if our memory model actually got it wrong and chose the wrong branch. It's we lost only 5 nanoseconds. If the data that we need to pull out is in level 2 cache, 7 nanoseconds. If we need to actually apply the mutex, synchronize that is. We use synchronize in our code, and now we need to actually play with all the acquiring log, relieving log, and all that. We are 25 nanoseconds worse. So, this is the very concept where actually mechanical sympathy came from. With data distance, varying so much, with multi-core processors being so important right now, occasionally we can't afford to program without knowing about them. So occasionally you will write code which you will want to not just run fast, you will want it to run blazing fast. And then you will need to know that, you will need to know which buffers actually flush which caches, where the cache coherence protocol actually comes into play, and where it starts exchanging messages, so that every single core will see the same value. And the cache coherence protocol is something that Java Virtual Machine is actually triggering behind the scenes with barriers, memory barriers. So the first tip that I would like you to take home, know thy cache lines. You are programming for some machine. This machine has a given architecture, which means that it will have limited cache lines, and those cache lines usually will have either 64 bits or 32 bits or blah, blah, blah. Now, know this and be aware that you code with awareness of this fact. Try, for example, to choose variables which will fit one cache line. Because most cache coherency protocols are heavily reliant on being able to just pull a line. So if the data that you're using actually spans across more than one line, the cache coherency protocol will have a number of problems with actually taking the data and transferring it fast. Martin Thompson is the proponent of mechanical sympathy. He's also the creator and moderator of one of the best places on the planet to actually gain data about it, which is the mailing list, Mechanical Sympathy. Lately, he's known for Aaron Protocol, but that's another matter entirely. So we're arriving at the most crucial part of the talk. I'm trying to pump some fresh air so that you guys will have better concentration. I'll leave it open even. This long quote by Doug Lee boils down to a very simple thing. Build down a small repertoire of constructs with which you will be able to determine how Java memory model actually works on a given combination of operating system, JVM, and your code. Why such answer? Basically, the small repertoire of constructions, which is written here, are things like have a small piece of code that uses, for example, double locking, so that you can see when double locking works and when it doesn't work. Have a simple piece of code which you know that usually should be reordered in this or that way, so that you can run it on JVM and see that, it's ordered differently. And so on and so on. Why? Because if you will have such a probe set, then you will be able to quickly tell whether, for example, you, for some reason, this or that optimization doesn't work. If you actually build an application which relies on that optimization, because you're, say, in Forex trading or low latency Java, and you need this optimization to work, then you may quickly know that you need to change your hardware or you need to upgrade the JVM. Most advanced Java threading library is Quasar. Who here heard of Quasar? Okay, 2 hands. So, who here heard of Go? Go language. More hands. So, Go language has a concept of Go routines. Go routines are pretty much green threads. These are small abstractions over threading, and they remain in the user space while they are able to actually work for you in parallel or concurrently. Now, Quasar does the very same thing, but for Java. Their threads are called fibers, and they are abstraction over both green thread and native thread. So you can actually write your code and create a fiber where you would usually create a thread, and then you run up the operations on this fiber, and sometimes it will be just a fiber, and sometimes you to be a native thread, this also can be arranged. The API and application is really, really nice. It's also open source, so pretty much easy. So mechanical sympathy, summary. If you missed a cache line, it hurts. The most basic example of missing a cache line is, for example, using an integer for a counter. When you know that your cache line is 64 bits, then you will need to actually have the remaining cache line filled with some other information, which is, of course, well, okay, that's not really a cache line miss, it's cache line fill, sorry, my bad. And now the example on the cache line after the talk, because it escaped my head at the moment, sorry. When you're actually taking a look at the cycles, cycles are important. If you can actually have the data in the cache, have it in the processor cache so that it will be accessed quicker. If you have the data in the main memory, it's like order of magnitude slower. If you have the data on the disk, oh my God, forgot about speed. Really forget about speed if you have your data on the disk and you need to go to the disk each time. Level 1 and level 2 caches are cheap. However, they will call for your cache coherency protocols because level 1, level 2 caches are per core. So core number 1 will not know what is in cache level 1 and 2 for other cores. Finally, when I said that Java memory uses barriers, now the catch is not every hardware that Java runs on has barriers instructions. Also, some hardware have so many barriers instructions that Java actually needs to work around them. This is also why Doug Lee proposed to have a simple set of probes which you can actually launch on your hardware, because if your hardware changes, your memory model will most likely change as well. For more reading. Well, the presentation wouldn't have happened if not for JavaDay 2014, where I did a lightning talk, and people came to me and told me that I should actually make it longer. So if any of you actually seen both the lightning talk and this talk and will have feedback for me, I will be most grateful. Jarek Pałka, who made me present for the first time. Also, Leslie Lampert's works on distributed systems, Bill Pugh's works on JSR 133, and Sarita Adve's papers are things which without them, I wouldn't be able to actually show anything. If you want to read more, then first of all, Martin Thompson and Mechanical Sympathy blog, JEPS 188, which is the new improvements in the Java memory model which are coming, Gets and All Java Concurrency in Practice, also called the book for concurrency in Java. Halili Shavit, The Art of Multiprocessor Programming. It is really a tough book, but to be honest, it's referenced in pretty much by everybody else on this page. Sarita Adve, Shared Memory Consistency Models, a tutorial. Jeremy Manson, Special POPL Issue, the Java Memory Model. And Huseman Petri, JMM, a formal explanation. Finally, like a month and 2 weeks ago, Alexei Shipilev made a really nice and illuminating blog post about Java Memory Model. And I really like the start of it. He quoted several tweets, like a tweet from himself: Alexei Shipilev has changed his relation with Java Memory Model to no longer certain. And a reply by somebody else: well, it's obvious, relationships are built by bridges, not by fences. So, about laws, there is pretty much everything that you want to know about the laws you will get from Wikipedia. But if you want more, there is a couple of press releases and articles, for example, about Gustafsson or pleasantly parallel problems, which are so easy to be made parallel that it's almost embarrassing. And finally, Brett Victor's presentation, which has a very nice transcript. Threads, task, green threads, and quasar within those two links. Finally, special thanks to people who actually helped me with a number of questions that I had when I made this presentation. And you, even the air wasn't needed, you persevered. I'm proud. Thank you.
Thank you, Tomasz. Maybe questions?
Thanks a lot. So just one comment. It would be great if this presentation included, included some small piece of code that is actually thrashing caches. Just because it's really simple code, and if you had like one slide for good code and another one for bad, it would be great.
For which parts of it? Like the optimizations or the...
No, I mean when the cache behavior is bad, like it is slow, and you show some benchmarking that it is 10 times slower, see? And another one where it's really fast because you adhere, you know the rules, and you play by them.
Noted. Come select some... Select yourself some swag.